Section: Introduction. In this section, we delve into the realm of deep learning models. These models have gained widespread use and can outperform human experts in various tasks. However, their complexity often makes it challenging to understand how they make decisions. As these models are increasingly applied in real-world scenarios, there is a growing need to unravel their inner workings for easier troubleshooting and a clearer grasp of their limitations. Model explanations come in various forms, such as input features, prototypes, or concepts. While methods focusing on low-level features can encounter issues like confirmation bias and lack of faithfulness, concept-based approaches offer explanations using familiar high-level terms. One popular method is concept activation vectors, CAVs, which represent a concept in the activation space of a specific layer using a probe dataset of concept examples. Despite their benefits, concept-based methods face challenges, including sensitivity to the specific probe dataset. In this paper, we concentrate on understanding three key properties of concept vectors: inconsistency across layers, entanglement with other concepts, and spatial dependence. We provide tools to analyze each property and demonstrate how they can impact testing with CAVs, TCAV. To mitigate these effects, we suggest creating CAVs for multiple layers, confirming expected dependencies between related concepts, and visualizing spatial dependence. These properties do not discourage the use of CAVs. Instead, they can help us better comprehend model behavior. For instance, we introduce a modified version of CAVs that are spatially dependent and can identify translation invariants in convolutional neural networks, CNNs. To explore these properties further, we developed a customizable synthetic dataset called Elements. This dataset enables researchers to investigate the faithfulness of concept-based explanations and the entanglement of concepts in a network. Moving on to the background, a CAV represents a concept in the activation space of a neural network layer. It involves mapping input to a vector in the activation space and then to the output. To create a CAV for a concept, a probe dataset with positive and negative samples is needed. By training a binary linear classifier on the corresponding activations, the CAV is obtained. To assess a model sensitivity to a CAV, testing with CAVs, TCAV, is introduced. It evaluates the model's conceptual sensitivity across a class by measuring the fraction of inputs positively influenced by the concept at a specific layer. In our study, we focus on three hypotheses related to CAVs to gain insights into network representations and the information encoded by concept vectors. These hypotheses are crucial for understanding and effectively utilizing CAV-based explanation methods. Section Summary. In this section, we delve into the complexities of deep learning models and the challenges in explaining their decision-making processes. We explore the limitations of low-level feature-based explainability methods like saliency, which can suffer from biases and lack complete faithfulness. To address these issues, we introduce concept-based methods like concept activation vectors, CAVs, which provide explanations using high-level human-understandable terms, although they come with their own challenges such as sensitivity to specific probe datasets. Section: Consistency. In this section, we aim to understand the behavior of models by exploring the concept activation vectors, CAVs, and their relationships across different layers. It is challenging to analyze all layers due to computational constraints, so we investigate how CAVs in different layers impact the model output. The TCAV scores are influenced by how the model output changes when the activations are perturbed in the direction of a CAV. If two CAVs from different layers have a consistent downstream effect on the model output when activations are perturbed in their direction, they are considered consistent. Our first hypothesis is that concept representations are consistent across layers. We also delve into the concept entanglement, where a CAV may encode multiple concepts simultaneously. We define entangled concepts as CAVs that are more similar to the activations of images containing certain concepts than those not containing them. Our second hypothesis explores this concept entanglement. Furthermore, we investigate spatial dependence on concepts by considering datasets containing the same concept but in different locations. We analyze how spatial dependence in the activations can lead to concept vectors with spatial dependence. Our third hypothesis questions whether concept activation vectors can be spatially dependent, which we later reject by examining the influence of concept location on spatial dependence. This rejection leads to the introduction of spatially dependent CAVs for testing a model's translation invariance with respect to specific concepts and classes. Section Summary. In this section, we investigate the consistency of concept activation vectors, CAVs, across different layers in a model. We explore how CAVs found in different layers can have the same impact on the model output, termed as consistency, and propose a hypothesis to test this relationship. Additionally, we delve into the entanglement of concepts within CAVs and the spatial dependence of concept vectors, proposing hypotheses and methods to analyze and reject them in subsequent sections. Section: Elements, a configurable synthetic dataset. In this section, we delve into exploring the hypotheses on consistency, entanglement, and spatial dependency. We conduct experiments using concept activation vectors, CAVs, on both the elements and ImageNet datasets. The details of our implementation can be found in the appendix of the paper. We kick off by investigating the first hypothesis, NH1, which posits that CAVs exhibit consistency across layers. This means that the effect of a concept vector on the model remains the same across different layers. To simplify, if we apply a concept vector, v_c_l_1, in one layer and another concept vector, v_c_l_2, in a different layer, the impact on the model should be consistent. We introduce linear perturbations hat_a_l_1 and hat_a_l_2 to the activations in layers l_1 and l_2 respectively. Our goal is to determine if the concept vectors v_c_l_1 and v_c_l_2 have the same influence on the activations and consequently on the model. If the model's function conserves vector addition, such as in a linear layer, then the effect of the concept vectors across layers remains consistent. However, if the function does not conserve vector addition, we cannot guarantee this consistency. In practical terms, this means that for certain activation functions like ReLU and sigmoid, it is impossible to have consistent concept vectors across layers. Our analysis aims to shed light on the practical challenges of maintaining consistent concept vectors in neural networks. Section Summary. In this section, we introduce a new synthetic dataset called Elements that allows us to control the training dataset and class definitions, influencing model properties like concept correlation in the embedding space and testing concept vector properties such as spatial dependence. By varying properties like color, brightness, size, and shape for each element in the dataset, we can configure it to explore consistency, entanglement, and spatial dependency of concept vectors across layers, providing insights into model behavior and interpretability. Section: Experiments. In this section, we aim to investigate whether the concept vectors obtained using TCAV are consistent. We assess the consistency of two perturbations by calculating the consistency error. To ensure that the perturbed activation remains within a certain range, we use a scaling term on the concept vectors. If two perturbations have a consistency error of 0, it means they have the same impact on the model. When using TCAV, we may not find a concept vector that perfectly aligns with another one. Therefore, we employ gradient descent to minimize the consistency error, which serves as a lower bound. The projected CAV measures the error between the activations of two layers, indicating how consistent the vectors are when projected into the next layer. If vector addition is preserved, the projected CAVs would have an error of 0. We also include random benchmarks to compare the consistency error. The experiments show that the concept vectors across different layers are not entirely consistent. The optimized CAVs have a lower error compared to the random CAVs, suggesting that the standard approach may not find optimally consistent vectors. However, finding completely consistent vectors in these layers seems challenging. The inability to find consistent concept vectors implies that the directions represented by the vectors in different layers are not equivalent. Furthermore, we explore the entanglement of concepts, where different concepts may be associated with each other. By analyzing the average pairwise cosine similarities between CAVs, we visualize these concept associations. The experiments reveal varying degrees of association between concepts in different datasets, indicating the presence of entanglement. The entangled concept vectors can impact the TCAV scores, leading to potentially misleading explanations. For instance, in the presence of associated CAVs, the model may assign high TCAV scores to certain concepts due to their interdependence, even if they are not directly relevant to the classification task. Section Summary. In this section, we investigate the consistency of concept vectors found using TCAV by measuring the consistency error between perturbations. We explore different methods like optimized CAV, projected CAV, and random CAV to assess the consistency of concept vectors across layers, revealing that the inability to find consistent vectors suggests that different layers encode different components of the same concept. Additionally, we delve into the entanglement of concepts, showing how associations between concepts can impact TCAV scores and lead to potentially misleading explanations in model interpretations. Section: Spatial Dependence. In this section, we investigate whether CAVs exhibit spatial dependence. We reshape the CAVs back to their original shape and calculate the channel-wise norm. This norm helps us determine if a CAV is spatially dependent by looking at how it varies across different dimensions. Visualizing the spatial norms of CAVs can show us which regions contribute most to the TCAV score. To create spatially dependent CAVs, we used specific probe datasets for elements and ImageNet that controlled the location of concepts or grayed out parts of images. When we used a spatially independent probe dataset, the spatial norms of CAVs were uniform, indicating no spatial dependence. However, when the probe dataset showed spatial dependence, the resulting CAVs also exhibited spatial dependence. This means that certain regions of the gradients did not contribute to the TCAV score. We then explored whether the model's sensitivity to concepts varied based on their location in the input image. We found that the model is not translation invariant if pixels in different locations affect activations differently and if each slice of activations affects the output differently. By analyzing the spatial norms, we confirmed that the model has activation spatial dependence. We also calculated TCAV scores for different sets of spatially dependent CAVs to see if the model sensitivity changes based on concept location. Our results showed that the model is not translation invariant with respect to certain concepts, as the sensitivity varied depending on where the concept appeared in the image. This suggests that CAVs can help detect model translation invariance. We recommend considering consistency, entanglement, and spatial dependence when using TCAV to avoid drawing incorrect conclusions. By visualizing concept vector spatial dependence using spatial norms, practitioners can better understand how concepts interact in the model.